Welcome to H2O, the A to Z of chemistry. I'm Dr. Ritu Johar, your educator for this course. States of matter. Today we begin with lecture 4 from the course, but make sure you watch the previous ones before viewing this one. In the last lecture, we started the discussion on hydrogen bonding. So I'm going to carry that further. You have understood what is a hydrogen bond, what are the conditions essential for the formation of a hydrogen bond, and also you learned the classification or the various types of hydrogen bonding that we have. So in this lecture, we will be developing an understanding on the applications of hydrogen bonding, and this is going to be really important lecture for you people because here you are going to understand many answers to the questions which are asked in the examination. Okay, so please be with me, be very attentive and have a thorough understanding of the concept. And when I'm giving you examples of the hydrogen bonding, these are not going to be the only examples that we have for hydrogen bonding. In 11th and 12th, you are going to study a lot of organic chemistry and inorganic chemistry, which is full of examples related to hydrogen bonding. And this you will be learning as the courses are going to progress and you are going to learn more about. But here you are at least going to have a glimpse of the very important applications of hydrogen bonding. Now, when we talk about the applications of hydrogen bonding, we study and understand the effect of hydrogen bonding on the properties of compounds. And these effects of hydrogen bonding on the properties is what is asked in the examination. Okay. And the first effect that we study is on the physical state of matter. And more is going to be the number of hydrogen bonds within a molecule. More compact is the structure going to be. For example, the first important example that we can understand is that of water. Water is what we drink. We cannot live without water. And water has its property of being in the liquid state as well in the solid state because of hydrogen bonding. Right? Both ice and water, they have hydrogen bonding. So let us first of all see the hydrogen bonding in liquid state of water. So the water molecules, they are going to be close to each other, but they are not very close to each other, right? In the liquid state, the molecules, they are close to each other, but they are just randomly placed here and there. Fine. And the molecules, when they're going to come close to each other, what we see is that the water molecules, they are going to form hydrogen bonds. So what are we going to see? We see that water, the oxygen of water, this is going to have a partial negative charge which is going to be equal to the 2 units of partial positive charge on the 2 hydrogen atoms. So there is a, you can say 2 unit partial negative charge on oxygen. So this is going to be responsible for forming 2 hydrogen bonds with 2 adjacent molecules hydrogens. So we have one hydrogen bond, we have the other hydrogen bond. Similarly, the hydrogens of the water molecule, they are going to form hydrogen bond with the oxygen of the other molecules. So 1 and 2. So as a result, we have 4 hydrogen bonds formed by one water molecule. And please, this is really very important. This is asked in the IIT examination in, I do not remember the year, but it has been asked. So you remember that 4 bonds, hydrogen bonds, are being formed by the water molecule. Okay. Now, so the water molecule, because of these hydrogen bonds, they are close to each other and we have the water in the liquid state. Had these hydrogen bonds not been there, the molecules there would have been far away from each other and we would have had what? We would have water vapors only. Fine. Next we have is the solid state of water. Now, generally what we see is when the molecules of the same compound, they are in the solid state, the molecules, they're going to come closer to each other. So when they come closer to each other, the density is going to be more in the solid state than the liquid state because there are more number of molecules per unit area. But what we see in the case of water is that the density of ice is less than that of water. Right? So this is one question that is asked in the examination. Why density of ice is less than that of water? Or another question that is asked is, why does ice float on water? So ice floats on water because the density of ice is less than that of water. But now why is the density of ice less than water? Well, this density is less because of the open cage crystal structure of ice. And what do we mean by this open cage crystal structure? If you see the structure of the ice crystal, here we have again water molecules arranged in such a particular fashion by the virtue of hydrogen bonding that there are large open spaces in between these molecules. So you can see this is one molecule of water which is going to form again four bonds with the other adjacent hydrogen water molecules, but in the result of the formation of this crystal there are large open spaces, and as a result the number of molecules per unit area is going to be less, and therefore the density of ice is going to be less. And if the density is less, water is ice is going to float on water, and this ice floating on water, this has a very important significance also. What is the significance? Let me explain you that also. When the is going to be the winter season, so in what is going to happen at very cold areas, the water is going to freeze. When water is going to freeze, because ice is less dense than water, so the surface water is the first that is going to freeze, and when that is going to freeze, there is going to form a ice layer on the surface of water, and this acts as an insulation between the atmospheric air and the water. And here then the whole of the water, this is not going to freeze further, and the water organisms, the aquatic organisms, they can live inside that water, right? So it is very important for us, this hydrogen bonding. So I hope you can understand. The next thing we have over here is this HF molecules. So again, lot of things coming with the HF molecules. Why this is so, this HF is very important is because this is the maximum polar molecule that we have. Fluorine, the most electronegative element in the periodic table, and hydrogen being the most electropositive element of the periodic table, right? So when these are going to form a bond, this is going to be a maximum polarity that we are seeing in a bond. And when this is forming hydrogen bonds with the other molecules, so here this hydrogen bond, this is going to be the strongest bond. But what we see is that HF, this exists as a liquid, whereas water, this can exist as solid ice. What should have happened is, when there are going to be more forces of attraction between the HF molecules, this should have existed as a solid rather than water existing as a solid. But what we see is it is happening the opposite. And why it is happening the opposite way around is because the HF molecules, they can form only two hydrogen bonds. Per molecule, there are going to be only two hydrogen bonds which can be formed, whereas in the case of water, four hydrogen bonds that we already have discussed. So one water molecule, this can form four hydrogen bonds, two with the hydrogen atoms, and one this oxygen is forming with the two hydrogens of the next one. So ultimately we can see that there is going to be formation of four hydrogen bonds per water molecule. So more is going to be the number of bonds, more closer are the molecules going to be, and therefore water can exist in the solid state, whereas HF, this is existing in the liquid state. Similar reason we can give for water existing as a liquid, whereas H2S existing as a gas. In case of H2S, the electronegative atom is sulfur. Sulfur is going to be electronegative. There is going to be a dipole-dipole interaction between the various molecules, but then the dipole-dipole interactions, they are weak. Sulfur, this cannot form hydrogen bonds with the adjacent molecule hydrogen, right? So this is a third period element. This is large in size, so this is not going to fit into the category of those molecules, those atoms of the molecules where hydrogen bond formation is favorable. The hydrogen bonds, they are generally seen for which atoms? Hydrogen and fluorine, oxygen or nitrogen. So please do remember, H2S molecules, they are not going to form hydrogen bonds, and water, this can form hydrogen bonds, so this is going to exist as a liquid, whereas H2S is a gas. The next property hydrogen bonds can influence is the melting and the boiling points. Now what is melting point? It is that temperature at which a solid is getting converted into its liquid state, and boiling point is that temperature at which a liquid is getting converted into its gaseous phase. So what we have is a solid is getting converted into a liquid is getting converted into a gas. And how is that going to happen? When the molecules in the solid, they are going to move away from each other, that is the point then when they are going to get converted into a liquid state. And when they're going to move further away from each other, it is that point at which this liquid is going to get converted into the gaseous state. So if the molecules, they have to move away from each other, if the intermolecular forces are going to be less, the melting and the boiling points are going to be less. If the intermolecular forces are going to be more, the melting and the boiling points are going to be more. So if there are hydrogen bonds present, the melting and the boiling points are going to increase because the hydrogen bonds, they are strong bonds, right? So they are the strength of the hydrogen bonds, this is more than the van der Waals forces of attraction. So if there were just simple van der Waals forces of attraction, the melting and the boiling points would have been low. But because now in the molecules, when hydrogen bonds are present, these are going to be strong bonds, we will have to spend more energy to move the molecules away from each other. So the melting and the boiling points, they are going to increase. For example, we have water, we have methyl alcohol, we have dimethyl ether. Now these compounds you will be able to appreciate more when you study organic chemistry. Okay, but just remember, water is going to show the maximum hydrogen bonding, then this methyl alcohol, and then the dimethyl ether, this does not show hydrogen bonding. Now this you can understand why methyl alcohol will show hydrogen bonding, because oxygen and hydrogen is forming a covalent bond. So hydrogen bonded covalently to a electronegative element, this can show hydrogen bonding, but this will be less than water, where one molecule is forming 4 hydrogen bonds. And then if you see this compound over here, this is oxygen in the center, but this oxygen, this is covalently bonded to carbon on either side. This CH3, this does not mean that this bond is between hydrogen and oxygen. Actually this bond over here, you will understand this in organic chemistry, the bond is between oxygen and carbon on either side, and it is this carbon which is covalently bonded to the 3 hydrogens, and this side also carbon bonded to the 3 hydrogens. Okay, so we have carbon and hydrogen bonds over here, and carbon and hydrogen, they have similar electronegativity values, so there is going to be equal sharing of the electrons. This bond between carbon and hydrogen, this is not going to be a polar bond, so we cannot have this hydrogen forming hydrogen bonds. So please do understand this thing very well. Carbon and hydrogen, they are forming a covalent bond. Hydrogen is not bonded to oxygen, fluorine or nitrogen. So this case, hydrogen bonding is not going to occur. Between these molecules, there will be only van der Waals forces of attraction, and therefore the melting and the boiling points, they are going to be the least in this case. The next we have is RCOH, which is carboxylic acid, and ROH. When we take these of comparable molecular weights, what we find is, because of hydrogen bonding, RCOH, this is going to have more melting, higher melting and boiling points. Then we have the corresponding alcohol ROH. Okay, so this again you will be able to understand better when you know the structures well, but just remember these things over here. The next we have is trihydric alcohols having melting and boiling points greater than dihydric alcohols, which are going to be having greater melting and boiling points than monohydric alcohol. Now when I talk about monohydric alcohol, this is this general formula ROH, where we have one OH per molecule. Okay, so one OH per molecule, this is going to have two OH groups per molecule, and this is going to have 3 OH groups per molecule. So you can understand over here that when there are going to be 3 OH groups, 3 hydrogens covalently bonded to oxygen, this can form more covalent bonds, so more are going to be the melting and the boiling points. Next we have is the primary amine, the secondary amine and the tertiary amines. In the primary amine, the general formula is RNH2. So we have 2 hydrogen which are covalently bonded to the nitrogen atom. In the secondary amine, there is 1 hydrogen covalently bonded to nitrogen, and in tertiary amine we have no hydrogen covalently bonded to nitrogen. So where is going to be hydrogen bonding being the maximum? In the primary amine, where we have 2 hydrogens covalently bonded to nitrogen, right? So I hope you can understand the primary amines, therefore they are going to have higher melting and boiling points than secondary, and tertiary amines, they do not have hydrogen bonding, so they will be having only van der Waals forces of attraction, which are weak forces, so low melting and boiling points. Next we have is the intramolecular hydrogen bonding. When this is occurring in the molecules, this is going to give a ring-like structure, right? So when it is going to be a ring-like structure, the hydrogen, if it is even attached to an electronegative element, then also we will be seeing that this would be forming the hydrogen bond inside the molecule only. It will not be able to form hydrogen bonds with other molecules, and therefore only weak van der Waals forces will be existing in the molecules. I will give you one example also before I wind up with this lecture. But just remember over here that only van der Waals forces, they are going to exist. Therefore the melting and the boiling points, they are going to be low in case there is intramolecular hydrogen bonding present. Now there is one question for you. We have to arrange the following compounds in the increasing order of the boiling points, right? So we have HF, we have HCl, we have HBr, we have HI. Now, what you should remember over here, first of all, is, although we have not discussed this, that the boiling points and the melting points, they are going to depend on the molecular mass. More is going to be the molecular mass, more is going to be the van der Waals forces of attraction. This you will be understanding in the next lecture when I talk to you about the characteristics of the van der Waals forces, and also I would be giving you the application of the van der Waals forces. But now, because we have not done that, just remember that the molecular weights, they are going to be directly proportional to the van der Waals forces. So more are going to be the van der Waals forces, more is going to be the melting and the boiling points. So the order should be what? It should be HF being the least, then HCl, then HBr, and then HI having the maximum boiling point, because iodine will be having the maximum atomic weight, right? So HI, this will be having the maximum molecular weight. So this should be the order, but what we see in this order is that HF, this has the highest boiling point. Why is it going to be so? I hope you can now understand, because we have hydrogen bonds in the case of HF. Because of HF hydrogen bonding, the forces of attraction between the molecules, this is going to be more, so the boiling point is going to be maximum for HF, then it is going to be HI, HBr, and the least boiling point will be for HCl. So I hope this is clear. The things are becoming clear to you people. Very nice. Now the next thing is, we have the molecular weights being influenced by hydrogen bonds. So whenever we have hydrogen bonding taking place, the molecular weights, they can increase. For example, what we have is, when we do an experimental finding of the molecular weight of acetic acid, which is CH3COH, what we find is that the molecular weight of CH3COH, which is acetic acid, what it is called, so acetic acid molecular weight comes to be twice the actual molecular weight. Now what is the molecular weight of the any compound? It is going to be the sum total of the atomic weights of these atoms over here, right? But what we find is that the molecular weight comes out to be twice as we calculate it from the molecular formula. Why is it so? It is because of a dimer formation taking place due to hydrogen bonding. So we have this acetic acid RCOOH. Okay, so here you can see there is a bond, covalent bond between oxygen and hydrogen. So this hydrogen, this is attached to a electronegative atom by a hydrogen bond, and then we have the adjacent molecule. In the adjacent molecule, there is oxygen present, which is an electronegative element. So this hydrogen and this oxygen, they can form a hydrogen bond. Similarly, on the other side also there is a hydrogen bond formed. So these two molecules, they form a dimer. Dimer means two molecules existing together. Okay. So because of this, when we do an experimental analysis for finding the molecular weight of acetic acid, we find it twice the actual molecular weight which should have been. More of this you will be able to understand when you're going to do a course on solutions in class 12. But at least you can now appreciate that this molecule, this is not existing as a single molecule, it is existing as two molecules together. Okay. So the next property which is influenced by hydrogen bonding is the solubility of the compounds. Now what we have learnt while we were studying the course on chemical bonding was that we studied the properties of the ionic compounds and the covalent compounds. There we learned that the ionic compounds, they are soluble in water being a polar solvent, whereas organic compounds, they are generally insoluble in water. And there then we developed the understanding the organic compounds which are going to be polar, it is going to dissolve in the polar solvent, that is water. But the non-polar organic compounds, they do not dissolve in water. But here also, now what we have is that when the non-polar organic compounds, they can form intermolecular hydrogen bonds with water, then these will be soluble in water. For example, one example that we have already learned is alcohol soluble in water, and that is because of this hydrogen bonds that they are present between alcohol and water molecules. Okay, so the alcohol molecule hydrogen covalently bonded to oxygen, the water molecule having electronegative oxygen, this is going to form a hydrogen bond, and when hydrogen bonds are formed, the alcohol is going to be soluble in water. Similarly, we have acetic acid. So we just now saw the structure of acetic acid, CH3COOH. So again, this hydrogen, this is covalently bonded to electronegative oxygen, and here again we have an electronegative oxygen. So hydrogen and oxygen, they can form the hydrogen bond, and therefore acetic acid is going to be soluble in water. Similar to this, we have glucose and fructose as organic compounds, but again because of the virtue of the hydrogen bonding taking place, these do dissolve in water. Next we have is the ketones, the ethers, the alkanes, which are insoluble in water because there is going to be no hydrogen bonding. Now again, the structures of these you will be able to understand once you have done organic chemistry, but then if we just have a look again at these molecules, here we have this hydrogens covalently bonded again to carbon, this also hydrogens covalently bonded to carbon, and the hydrogens which are covalently bonded to carbon, they are not going to participate in hydrogen bonding, right? Excuse me. Similarly, we have ether. So again in ether, the hydrogens, they are covalently bonded to carbon. In alkane, again a carbon hydrogen bond. So these molecules, they do not have hydrogens participating in hydrogen bonding. Therefore, they are going to be insoluble in water. Okay. The next we have is the ammonium ions and the sodium ions, which is going to be more soluble in water. So ammonium ions, they are more soluble than the sodium ions in water. Why? Well, this is again because that if we consider the sodium ions and water is going to be what interaction? It is going to be an ion and a dipole interaction. And ion dipole interaction are what type of interactions? These are van der Waals forces of attraction. So these are going to be weak forces. But when we consider the ammonium ions in water, this is going to be a nitrogen and hydrogen bond over here. So a hydrogen which is bonded to nitrogen, which is the electronegative atom. So when this is going to dissolve in, be soluble in water, the hydrogen over here, this can form hydrogen bonds with the oxygen atom of the water molecule. So this is a case of hydrogen bonding. This is going to be a case of a van der Waals force of attraction, which is going to be a stronger force. This hydrogen bonding is going to be a stronger force. Therefore, ammonium ions, they will be more soluble than sodium ions in water. Similar case, we can talk about the alcohol being more soluble in water than the amines. Why is it so? Because here what are you seeing? The hydrogen, this is covalently bonded to oxygen. Here hydrogen is covalently bonded to nitrogen. So this hydrogen, this can form stronger bonds than this hydrogen which is covalently bonded to nitrogen, right? Because oxygen, this is more electronegative than nitrogen. I hope again this is clear to you people. These applications, they are very important. You will be asked these when you're studying organic chemistry, and then you have already learned them. So this is going to be really very easy for you. Next we have is an example of intramolecular hydrogen bond. Now, if you see this compound, this is salicylaldehyde or orthohydroxybenzaldehyde. Now, two hydrogens you can see in the molecule, at least now. Well, if you draw the structure, you will be able to see more hydrogens also in the compound, but I am not interested in just telling you all about the structure in detail. That we will be talking when we discuss more in organic chemistry. Okay, so here we have this hydrogen which is covalently bonded to carbon. So can this form hydrogen bonds? No, this cannot form hydrogen bonds, right? So now you know all this. But when you see this hydrogen, this is covalently bonded to oxygen. So this should be able to form hydrogen bonds if we add this to water, right? So this is a hydrogen covalently bonded to oxygen. When we put it into water, then the compound should be soluble in water. But what we see is that this is not soluble in water. Why is it not soluble in water? Because this hydrogen, this is forming hydrogen bonds in the molecule itself. There was an electronegative oxygen present in the molecule, so this formed hydrogen bonds over here only, and now this is no longer free to form hydrogen bonds with the water molecules. So what is going to happen? The intramolecular hydrogen bonding, this has reduced the solubility as it has formed chelates. And this what meaning is, though we will be discussing more about it in further courses, but this is going to form ring-like structures, right? So this molecule now, this is a closed ring. The hydrogens, they are not available for participating in hydrogen bonding with other molecules, and therefore the solubility of these compounds, they decrease. Okay. The next property is viscosity. So viscosity is something that you will be discussing more about in physics, but now just in simple terms, if I talk about it, well, if a liquid is going to be thick, we call it as viscous. If it is not that thick, it is free flowing, then we call it as less viscous if we are comparing to, right? So when we see hydrogen bonding taking place, so the molecules, they will come close to each other, they will be associated together, and thus the viscosity is going to increase. So if you have to again compare these three compounds, we have water having the maximum hydrogen bonding, then methyl alcohol, and this dimethyl ether, where there is going to be no hydrogen bonding because the hydrogen, this is associated with carbon by covalent bonds. So this is going to have no hydrogen bonding. So this will be the least viscous, and water having the maximum hydrogen bonds, this is going to be the most viscous, right? Now, to sum up the whole lecture that we have learned, I have just one question for you. Which is more volatile, orthonitrophenol or paranitrophenol? And this is a question which is frequently asked in the examination. So that is why I have put it over here. Although there are going to be so many other questions related to hydrogen bonding, and these you will be learning further in the courses on organic or inorganic chemistry. Okay. So the question is again, which is more volatile, orthonitrophenol or paranitrophenol? And more volatile means which is going to evaporate fast, and evaporate fast is going to mean that which of these two compounds this has a lower boiling point, you can say. So let us see first of all these structures, because without organic chemistry you will not be able to tell the structures. So this compound over here is called as orthonitrophenol, and this compound that you can see, this is called as paranitrophenol. And well, if I differentiate both of them, this we have a OH group. This is a benzene ring that is present. Okay, so you will be seeing a lot about this in organic chemistry, and this is a benzene ring. Here we have a OH group, and adjacent to this OH group, this is a NO2 group which is present. And in this molecule, if you see, this is the OH group, and just opposite to this, exactly opposite to this, we have a nitro group. Okay, so now what you have to tell is which is more volatile, orthonitrophenol or paranitrophenol. Now just have a thought about it, and then I'll let you know the answer. Now, if you've thought about it, well, it is very good. Otherwise, do not worry. Just see what is going to happen over here. So if you see this compound, the hydrogen which was covalently bonded to oxygen, this was present in the near vicinity of this electronegative oxygen in the molecule itself. So this is a case of what? This is a case of intramolecular hydrogen bonding that is taking place, right? The other, if you see over here, well, this hydrogen which was covalently bonded to oxygen, this is far away from the oxygen atom, so this cannot form a intramolecular hydrogen bonding. So when we see the compound itself, there are going to be many molecules in the compound, right? So this molecule is going to associate with one more molecule of para-nitrophenol when they're going to come close to each other. So you can see this hydrogen covalently bonded to oxygen, and this oxygen over here is of the other molecule. So this is a case of intermolecular hydrogen bonding taking place. So intramolecular hydrogen bonding, when this is going to take place, if we have two molecules over here, what is the force that they are going to experience with each other? Well, this is going to be a van der Waals force of attraction that will be present between them. So when this is a van der Waals force, this is a hydrogen bonding taking place between molecules. This is going to be a stronger force. So stronger force means that you will have to spend more energy to separate these molecules. This can be separated easily because they are going to be weak forces. So weak forces, this compound is going to be more volatile. I hope you can understand now that orthonitrophenol is more volatile than para-nitrophenol, because in this case intramolecular hydrogen bonding is taking place, whereas in this case intermolecular hydrogen bonding is taking place. Another question which can be asked over here is, can these two compounds be separated by fractional distillation? Now, what do we have in fractional distillation is that while we are doing a fractional distillation, we can distill two compounds, we can separate two compounds when there is a difference in their boiling points. And now when these two compounds, we have already studied that this is going to boil off quickly, whereas this is going to take some time because of the intermolecular hydrogen bonding. Yes, they can be separated by fractional distillation also. So these are the questions which are frequently asked in the examination, and now I hope you can understand the value of hydrogen bonding. So that would be all for this lecture. Well, I'm not winded up with the topic of intermolecular forces. There is still to come. And along with that, in the next lecture, I am going to talk about another very important thing which is related to the states of matter, that is the thermal energy. So if you've liked this lecture, please do click on the like link. If you have not subscribed to the channel till now, please do that so that you get the important notifications related to the upcoming lectures. Please do click on the bell icon as well. Any doubts, most welcome. Please mail us at h2ochemistry@gmail.com. You can join us on the Facebook page of the channel by the same name, H2O Chemistry. You can also put your doubts in the comment section as well. We will be really glad to help you all. Thank you and have a nice day. God bless you.